limit as x approaches 0 from the right, from x to the x minus 1 divided by natural log x plus x minus 1. I think they meant x to the x. We'll see in a moment. There may be a typo in there. I'm not sure. Because we can't differentiate x to x. We have to use natural log, to differentiate that. So I'm not sure whether that's what they wanted in there, if there is a typo. Because we can't differentiate, right? Remember, y equals x raised to the x power. We have natural log x equals x times natural log x. We can't differentiate x raised to x. So when we plug in 0, 0 raised to 0 will be 1. 1 minus 1 is 0 indeed. Let's see what we have in the denominator. We have natural log from 0 from the right is infinity. 0 from the right is negative infinity. So the top is 0 and the bottom is negative infinity. Right? So if, although 0 raised to 0 is, I can't say it's 1, right? It's an indeterminate case on its own. So the top will be something I have no idea what it is, because I have not determined this. I have to determine the derivative. So we have to do that. So assuming that this, although I shouldn't assume, so the numerator will be 0, the denominator, this will be infinity, and this is nothing. Yeah, I'm not sure. I think there is it could be a possible error in there. So we can skip it for now. I'll think about it. But I just we can, as I said, we can differentiate. So if I differentiate, I get 1 over y times dy over the x, and this is natural log x plus 1. So then dy over dx is x raised to x, and then natural log x plus 1. Yeah, I have to put a question mark here on this one because of that x to the x. Okay, let's leave it for now. I promise to look at it and come up with an idea, or see if any of my colleagues found an error in this particular problem. Maybe they did. We did find some errors, and we do send them back to them. 38. Normally, TAs write solutions to these problems, and they check those. Okay, it doesn't sound right to me. So let's look at 38. Limit e to the x minus e to negative x and minus 2x. 38. That's the next one, 38. Divided by x minus sine x. And then x approaches 0. Okay. Any questions on? Did I copy it correctly? Always check for me. Okay. So when x approaches 0, let's see what the top is, where the top is going. E to 0 is 1. E to 0 is 1. 1 minus 1 is, and negative 2 times 0. Perfect. 0. How much is sine 0? Good. Another very friendly case. It's 0 over 0. We can directly use L'Hopital's rule. Limit as x approaches 0. E to the x prime. Perfect. But now when I differentiate e to negative x, it's e to negative x times negative x prime, which is very good. So it'll be plus e to negative x, and then minus 2. What about the denominator? 1 minus cosine x. Good. We try again. Let's see what we have. We cannot simply differentiate if there is no 0 over 0 or infinity over infinity. So don't assume that that will always work. Good. What is the top? This approaches 1. This approaches 1 plus 1, 2 minus 2. Excellent. Cosine 0, 1 minus 1. Good. Nice. Limit. X approaches 0. E to the x prime. But e to negative x prime will be e to negative x, but times negative 1. Negative e to negative x. Now the denominator. Cosine prime is negative sine with minus in front. Sine x. And 1 prime is 0. Okay, we try again. 1 minus 1, 0. The denominator, 0. Nice. One more time. Limit. X approaches 0. The top we know already. It's e to the x, but plus e to negative x. And the bottom is cosine x. And we hope that this is the end of it. So what is it? So the top is 2, and the bottom is? So it's 2. Now we're getting into more complicated situations. So let's take a look at 46. So far we still have not seen more than 0 over 0, infinity over infinity. And we've seen a long time ago infinity minus infinity. So let's look at 46. Same page. In 46 we have limit x tangent 1 over x when x approaches infinity. Okay.
Is that 10?
Yes, tangent. So tangent of 1 over x, and this is x times. So tangent applied to 1 over x. Let me check. Tangent applied to 1 over x. If you want to put it in parentheses, you can, if that's better. Good. So now let's try. Where does this go? When x approaches infinity, this quantity approaches. Perfect. Where does this inside tangent, where does this go?
0.
Perfect. How much is tangent 0? All this approaches.
0.
Indeed. Well, this is the next indeterminate case. 0 times infinity. You can say it's 0. No, it's not. So we'll go back. So we already seen 0, infinity over infinity, 0 over 0, infinity minus infinity, and this is the next one. 0 times infinity. This is number 4. They're not specifically numbered. Doesn't matter. However, I do have a problem with this. Why do I have a problem with this? It's because I cannot use L'Hopital's rule on 0 times infinity. However, it's a friendly situation. I can change it into infinity over infinity, or maybe 0 over 0, by a simple algebraic manipulation. And you'll tell me if you agree with this first, and then we'll check. Are they the same? Because if they're not the same, then we can continue. But when I divide by a fraction, I flip the fraction, right? And that's what I get. X times tangent 1 over x. So this is exactly the same thing with that. Would you agree, everyone?
Yeah.
Now I try again. If this new situation is not 0 over 0 or infinity over infinity, I cannot use L'Hopital's rule. But I know the top, we already know, approaches what?
0.
What about the bottom? When x approaches infinity, where does the bottom go? Right. So we made, by a simple algebraic manipulation, we change the indeterminate case, that is 0 times infinity, into something like 0 over 0, for example, in which we can use L'Hopital's rule. Excellent. So now, let's differentiate the top. So from here, we go here, and I have page 9. So limit as x approaches infinity. Can anyone give us the derivative of the top? Secant squared, indeed, of 1 over x times,
Negative.
excellent. You see how important this little 1 over x prime is, if we remember it. And now what is the derivative of the denominator, please?
Negative 1 over x squared.
And here's what I do. Lucky for us. So, secant squared 1 over x. When x approaches infinity, where we know 1 over x approaches 0. How much is secant 0? It's the same with 1 over cosine 0, right? Secant alpha is 1 over cosine alpha. If I know that this approaches 0, and which means this approaches 0, and I know cosine 0 is, then secant 0 must be 1 as well. So the answer is 1. You wouldn't have expected that 0 times infinity to give us 1. Yes, Vanessa?
Can you explain that part again? I don't understand.
Which part?
Like, secant.
Secant is the same with 1 over cosine.
Whatever cosine squared.
Yes, but it's the same thing.
Okay.
Yes, it's the same thing. So cosine, when 1 over x approaches 0, meaning alpha approaches 0, cosine squared approaches 1. But 1 over 1 will be 1. That's why secant 1 over x is 1. Approaches 1. It's not 1. It approaches 1 when x approaches infinity. Any questions? Okay. So we've seen one other indeterminate case. Let's look at a more complicated situation, but a simple one from the complicated ones, like 57. It's in red in your book. So limit 1 minus 2x raised to 1 over x when x approaches 0. This is not a friendly situation. Okay, ready? We have to check what it is. Where does this go when x approaches 0? You can say, oops, because we know the graph of this, right? So when x approaches 0 from the right, it's infinity. 0 from the left is negative infinity. Which one? It's D and E, right? But it's an infinity. Okay, so that top is infinity. 1 over x approaches infinity in this case. But where does 1 minus 2x go? To 1. So this is another indeterminate case. And you can say, really? Seriously? 1 to infinity? Yes, seriously. 1 to infinity. So please add it in. 1 to infinity is another indeterminate case. I would say the most difficult to work with, in my opinion. 0 times infinity is not such a big deal. But 1 to infinity, or infinity raised to 0 as the next one. So the power ones are the most difficult to work with. Okay, so let's go back. Okay, how on earth do I change this? But there is something that we had from our chapter 3 that was the, Vicky? Careful. Number 1 from this test, which I was hoping and no one will forget that there is no rule for a function raised to a function, and we have to employ something. Yes. We're back to the same thing. Because it's a function raised to a function. So I will have to denote by y 1 minus 2x raised to 1 over x. Have no choice. Okay, now what do we do next again? Excellent. 1 over x times natural log 1 minus 2x. And now, no, we're not going to differentiate because we're not asked to differentiate. We're asked to find the limit. And this time, I'm going to find the limit of this. And you should say, no, 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 no. You are not asked to find the limit from the log. You want to find the limit of the log? No, we don't agree with it, right? You shouldn't agree with it, correct? Because we're not asked to find the limit of the log. We're asked to find the limit of the function, not the limit of the log of the function. And then I will beg for a minute to explain, and you understand why we do that. So yes, we will determine the limit as x approaches 0 from the natural log of y. So I'm going to write limit as x approaches 0. Instead of natural log y, I'm going to write this, of course. It's the same thing with natural log y. So natural log 1 minus 2x divided by x. So keep in mind, I moved my topic, my target, from finding the limit of the function to finding the limit of the log of the function. So now we have this. Let's plug it in and see what we get. So the top goes to, when this is 0 and this is 1, natural log 1 is 0. And the bottom goes to, yay, I like this. Why do I like it? Because I can use L'Hopital's rule. And you can still say, we're watching you. You're doing something else that you are asked to do. Yes, I'm glad you're watching me because you're going to understand what happens in a minute. So then limit as x approaches 0. Please differentiate the top as if it's alone on the planet. 1 minus 2x multiplied by, excellent. The denominator prime, good. Let's write it one more time. Limit as x approaches 0. Negative 2 over 1 minus 2x. And please give me the answer. Do you all agree with negative 2? The top is negative 2. When x approaches 0, the bottom is 1. So negative 2 over 1 is negative 2. Would you agree? Now I'm going to copy the beginning and the end. Nothing in between. I will copy limit as x approaches 0 from natural log y equals negative 2. Let's discuss this. This is our result so far. It's not done, of course. Now, let me refresh our memory on a theorem that we have not used. I mentioned it several times, but we haven't really used it like we're using it now. This is an operator, limit, and this is an operator, natural log. Because this function is continuous, we've done this before. We are allowed to do something. What is that something that
Switch those operators.
swap them? Yes. I'm going to put the natural log in front of the limit of y. Excellent. Thank you for remembering that. Limit as x approaches 0 of y equals negative 2. I didn't need parentheses over there, sorry. And now the moment of truth. Natural log of what is negative 2? And this what will be this limit that I'm looking for. What should I have in here so that the limit is -2. E raised to -2, and -2 goes in front, and natural log E is? Excellent, well done. Indeed, e to -2. So then limit of 1 minus 2x to 1 over x when x approaches 0 is e to -2. You didn't expect that 1 to infinity to end up being e to -2. Honestly, you did not. Even if you say you did, I would not believe it. No one would have guessed that this indeterminate case in this situation turns out or gives us a result of e to -2. Do we understand why this is e to -2? Let me explain one more time just to make sure. If we apply natural log to e to the 4th or the 5th power, this becomes 5 natural log e. And natural log e is 1, that's why the answer is 5. So natural log e to -2 will be -2 times natural log e. But since this is 1, that's how we get the -2. Yes, Braden?
Why does the limit as x approaches 0 y go away? I give it crossed out.
Oh, no, I was just saying that this is what I'm after. This was the question from the very beginning.
Okay.
So I did not determine the limit directly. I determined the limit of the natural log. And once I got to this stage, knowing that this function is continuous, of course it is, then I was allowed to swap the two operators. I put the limit of the natural log outside and the limit inside, and I was saying this is what I'm after, not this. But it was easier to determine the limit of the natural log first, and then come up with a correct answer, say this cannot be anything else but e to -2. So that's how we got e to -2. We had so many different steps here. Again, this is not a trivial situation at all. Okay, we do have time, so let's choose one more like this, and then let's graph another function. Would you agree? Okay, would you like me to let you work on this for a moment on your own? Yes? No? Okay, so 62. One more time, this is not an easy situation. 62. Limit. As x approaches infinity. E to the x plus x. Everything raised to 1 over x. Okay, I want to add the last one here, which is 0 raised to 0. That's why when I saw that x raised to x, that's an indeterminate case. So that's why I will. So these are all 7 indeterminate cases. These are friendly. These are not. These are the most difficult ones, the power ones. And this is okay, and this is okay. These are the nicest. These two are okay, but these, the power ones, are the most difficult to work with. Did I copy incorrectly? I do that a lot. 62. X approaches infinity, e to the x plus x over and raised to 1 over x. Okay, let's get it started together. Where does this go? So this is infinity, infinity plus infinity is infinity. Where does this go?
0.
Good. So it's one of the power ones, ugly. However, for the power ones, we do have a treatment. What is the treatment called? The treatment is called natural log, right? For a power like this, right? So then we say y equals e to the x plus x raised to 1 over x. Our next step would be to write
Natural log y.
yes. natural log y equals 1 over x natural log e to the x plus x. Good. What do we do now? We created a new function, right? Yes, but eventually this will help us find what we're looking for. So, yes, Ricky? Very good. Limit x approaches infinity from natural log y, which I will replace by this, because natural log y is this. So limit x approaches infinity, natural log e to the x plus x over x. What am I hoping for at this point? That when I plug in infinity, my hope is or 0, correct. That's my hope. Let's see if we get it. So infinity. Inside the infinity, natural log, remember the graph? We graphed it several times. I forgot to graph it more often. That's the graph of natural log. So then the top goes to? Excellent. And the bottom goes to? Ah, nice. Good. So then differentiate the top because it's inside a limit as if it's alone by itself. I meant to say alone on the planet. So it's 1 over e to the x plus x times
e to the x
plus 1. Excellent. And the bottom?
1.
Ah, okay. Looks promising. Good. So this is limit. X approaches infinity, e to the x plus 1 over e to the x plus x. Okay, perfect. Then, yes, Vanessa?
I actually wrote it down at the bottom. Like the stuff that you just did. Why didn't you?
The denominator is 1, and this is over 1, so this goes to the numerator. This times this over this times 1. Just to make it as simple as possible. Okay, where does the numerator go? And the bottom. Okay, good. So then limit x approaches infinity, the top. We differentiate it as if it's by itself.
e to the x.
Good. The bottom.
e to the x plus 4.
Okay. Still infinity over infinity. The top will go to, yes. The bottom differentiated. Okay, and this is how much?
Infinity.
Right, but I'll simplify. They are the same. So the answer is 1. We copy the very beginning in which we wrote limit of the natural log y as x approaches infinity equals 1. What do we do next? Because all these functions, yes, Ricky? So you want to put natural log in front. Swap the two.
Yeah.
Good. So natural log of limit of y as x approaches infinity is 1. Question is, what could this be? And that's our answer for the problem we are working on. What could this be? Which number should this be so that natural log of it is 1?
0.
Natural log 0 is undefined. E indeed. This must be e. So then limit as x approaches infinity from e to the x plus x raised to 1 over x is e indeed. Is that clear, Brayden? Natural log of e is 1. There is no other number. Only natural log of e. Yes, Ricky?
Why is it?
Because there is no other number that you plug in natural log to get 1. Only natural log e is 1. Any questions?
So did the e and the natural log cancel out to be 1?
Natural log of e is 1. So that this number must be e. So natural log of the function that we are trying, limit of the function we're trying to find when x approaches infinity must equal e. Is that clear? Okay,
Why you can take the natural log out?
excellent, very good. A long time ago in continuity, I mentioned it, but we used it a few times, but not not as much as we are using it now. So in continuity, if you remember, we talked about this theorem, but I said I'm not going to say much about it because every time we're using it, we're going to refresh our memory on it. So as you see, the limit of a function, which in this case is our natural log, is the function of the limit of g of x. So if f is continuous and the inner function is also continuous, then we are allowed to swap the operators. In this case, we swap the natural log with the limit.
So you mean natural log?
Let me also give you another example before you ask your question. I'm saying this. Limit of the square root of a function as x approaches a is the same with the square root of the limit of the function as x approaches a. It's the same concept. So this is the operator, which in our case was natural log, and this is the limit. So because this function is continuous, I'm allowed to swap the two operators and put the square root outside. This was one of the limit laws. So for the same reason, natural limit of the natural log of the function is the natural log of the limit of the function. But it doesn't happen unless the function is continuous. So this was a theorem on the continuity. We did not really use it then. We used it when we learned the differentiation rules. And I said then, wait till we get to chapter 4, in which we are going to use it more frequently. Yes, Ricky, is this okay? So this was a limit law from chapter 2. So the limit law of the limit of the square root of a function, if the function is continuous, then I can swap the two operators. So the square root is like the natural log. Same thing, same idea. We also have this one. We didn't really use it in those terms, but it's the same thing. So limit of x to the third when x approaches 2 is the same with limit of x as x approaches 2, everything cubed. It's the same thing. I am swapping the operator for power 3 with the limit operator, putting the limit operator inside and the power 3 outside, which is the same thing. So I would get 2 to the third is 8. Or from here, 2 to the third, which is 8. Why? Because x cubed is continuous. Very good question. Is this better? Okay, very good. I knew someone would ask, and I'm happy you did. Okay. Let's finish up today with, I still have 10 minutes. Let's finish up with a graph. So that's section 4.5. I would like to show a graph with, but I don't. I need more than 10 minutes to show a graph with a slant asymptote. So let's just graph something simple, a rational function like 9. Hopefully we can finish in 10 minutes.
Is this 4.3 or
4.5.
4.5?
Yes, 4.4 was L'Hopital's rule with his 7 indeterminate cases. So x over x minus 1. We may be able to finish in 10 minutes or not, but I'm not going to rush through. Okay, so obviously we have to start with always with what? The
Domain.
very good. Perfect. What is the domain of this function? Can anyone identify? Excellent. So negative infinity, 0 has to be in the table at all costs. Even if the function is undefined there, 0 has to be in the table. I immediately know that there must be infinity left and right. I also know that x equals 1 is a vertical asymptote right away. Would you agree?
Yes.
Perfect. I don't know the signs. I'm going to determine the signs in a minute. Let's find those. I have to. Limit as x approaches 1 from the left, from x over x minus 1, and limit as x approaches 1 from the right, from x over x minus 1. I know the answer. I have no doubt. But I don't know the sign. So -1, because this is -1 and this is 0, and this is -1. This is 1 and 0 and 1 and 0. Obviously, infinity. So 1 from the left, 0.9. Please plug in 0.9 and give me the answer. And then plug in 1.1 and give me the answer.
Wait, wow, that
I'm sorry?
will that be infinity?
Because the top is 1 and the bottom is 0. So, and we already know that the function is undefined and 1, it has to be a vertical asymptote. And the same thing here, 1 over 0, so we know there is no hope. 1 over 0 means infinity. So please plug in 0.9 and give us the sign.
0.9.
Negative, and with 1.1, very good, very good. Excellent. Now we want this. What are these? Very good, and infinity and negative infinity. Limit, x approaches infinity, x over x minus 1, and limit x approaches negative infinity, x over x minus 1. You can say it's infinity of infinity, and now I know L'Hopital's rule. Good, that's fine. So then limit x approaches infinity, the top goes to 1, the bottom goes to, so the limit is, then there is no difference for the other one. What does that mean for the function? What does this mean? So this means that x equals 1 is a VA, and this means that y equals 1 is excellent. Well done. 1 and 1, y equals 1, horizontal asymptote. Perfect. Let's plug in 0 and give me the answer for 0. Yes, Braden?
I have a question.
Yes.
On why one of them is a horizontal asymptote and one's a vertical.
Because I'm determining limits left and right of a number to study the sign left and right. And this is the end behavior, which deals with infinities. Better?
Yeah.
Perfect. So please plug in 0 and give me the answer. It's 0, correct? There is nothing else I can find about the function from the function itself. Therefore, I will continue with the first derivative. So y equals x over x minus 1, y prime. Top prime, 1 times x minus 1 minus the top times the denominator prime. Excellent. Over x minus 1 squared. Okay, very nice. What does this mean? It means that the function has critical numbers or it does not. It does not, because a fraction is 0 only when the top is 0. The top cannot be 0. The function is undefined at 1, so is the derivative. So never 0. Can anyone give us the sign of this? Of the whole thing forever? Negative. Do you agree? Very good. Because this is always positive. Always positive. That's why I don't even care to plug it in. Since that is the case, I want to make sure that these two rows work well together. From 1 to 0, what does the function do? Is that supported by the sign of the derivative, the way we found it? Okay. From 0 to negative infinity, decreases. Is that supported by the sign of the derivative? From infinity to 1, is that supported by the sign of the derivative? Almost done. Let's look at the second derivative. So the first derivative is this. This is what I want to differentiate. I don't want to differentiate this. I want to differentiate this because it's easier. So the second derivative is, can anyone give us the answer? 2 x minus 1 to negative 3 times the inner function prime, but it's 1. So this is 2 over x minus 1 to the third. For the purpose of the sign, I will rewrite this as 2 over x minus 1 squared times 1 over x minus 1. Why? Why would I even do that or think of doing it? Because this is always positive. Don't even worry about it. I want to study the sign of this only. Back to the table. Plug in a number to the left of 1 in this portion only, and give me the sign. Negative indeed, right? Please plug in only in this portion a number to the right of 1 and give me the sign. Excellent. That's all I care about, and I can graph. When I graph a function with asymptotes, what do I have to graph first? Forever mandatory. First, the asymptotes. Very good. This function has 2 asymptotes. One that is vertical at 1, and the other one that is horizontal at 1. I will plot the points I have. Just 0, 0. That's the only point I have. I don't care for any information but what I see in my table. Ready? So, from approaching the asymptote, decreasing towards, opening downward, decreasing towards the origin, opening down towards negative infinity. From approaching 1, opening down, crossing at the origin, going to negative infinity on the left-hand side of the vertical asymptote. From 1 down to the origin, down to negative infinity on the left-hand side of the vertical asymptote. On the right-hand side, coming from positive infinity, decreasing to 1, opening upward. From positive infinity, decreasing to 1, opening upward. And this is the function f of x equals x minus 1. All the information is in our table. We do not need to do anything else or look anywhere else.